Well, hello, this is Mr. Doro. Today we're going to be talking about gases and mostly properties of gases. In chemistry, this is found in chapters 13 and 14, and honors chem is found in chapters 10 and 11. Well, we have to start out by talking about something called the kinetic molecular theory, which I'll abbreviate KMT. In the kinetic molecular theory, kinetic means motion, molecular means molecules, and theory means this is how we believe it happens. This is based on the idea that all matter is in motion constantly. And when we're talking about gases, usually we think in terms of ideal gases, which don't really exist, but they would fit all parts of the kinetic molecular theory perfectly. So here's my quick breakdown of the kinetic molecular theory. This is what it assumes. That gases, when we're talking about gases, since that's the unit we're dealing with, that there are a bunch of tiny particles that are so far apart relative to their size. Really, if we looked at them, we'd say they're packed really close together. But they're super, super tiny particles. And so we assume then, relative to their size, related to that they would be considered far apart from each other. And then when they collide with each other, that they're elastic collisions. Now, elastic collisions means they don't gain or lose energy. The energy is conserved the whole time. So when they hit each other, they just pass on that energy. They're in constant motion. They don't attract to each other, and they don't repel each other. And the temperature of those particles is dependent on the average kinetic energy. That means how fast they're moving. The higher the temperature, the faster they'll be moving. The lower the temperature, the slower they'll be moving. And that's all laid out in the kinetic energy formula. Ke, kinetic energy, sorry about that. Kinetic energy is found by 1/2 times the mass, and so the heavier they are, usually the slower they'll be moving, times the velocity, that's the v, squared. So it really depends mostly on the velocity, not as much on the mass. Well, one of the fun things about gases is all gases, no matter what they're made up of, have similar properties. Here are some properties of gases that you need to know. One thing is they expand to fit their containers. So whatever container they're in, they'll spread out so that they fill up the whole container. They're fluid, which means they flow. They can move past each other. They have low density. They're as far spread out as they can get. They exert pressure. Pressure is when they push on something, and so that's what gases do by moving around. They're compressible. Since they have low density, they have area in between them where you can push them together. And they go through something called diffusion and effusion. Diffusion means that if you have a couple different gases that are in the same container, because of their random motion, they'll spread out and intermix with each other. Effusion means that if you have a little hole in a container, like a little pinhole in a balloon, that eventually the gases will end up leaking out of there again because of their random motion. They'll find their way, they'll bounce around until they find a way out that little hole. All gases also have certain variables. Variables means things that can change for gases and things that you can measure too. And so you're going to want to make sure you have these down, these variables for gases, along with the units, because these are kind of important when we're working with gas laws. The first one is volume, and that's the amount of space it takes up. And the units are either liters or milliliters or centimeters cubed, that's a cube, or decimeters cubed. Anything cubed is going to be volume, or anything with liters is going to be volume also. The next one is pressure. That's the amount of force that it exerts on an object. And these units are a little bit different, things you might not have heard of before. ATMs, which are atmospheres, millimeters of mercury, torr, Pascal, PSI, and there are others, but we'll just use those for right now. Temperature, the amount of kinetic energy something has, and that is, these are not units, these are what the symbols are, T, V, and P, and that unit for gases has to be in something called Kelvin, K. And how do you find Kelvin? Well, if you're given degrees Celsius, you have to multiply it by 273. And finally, the last one is the number of moles, and the number of moles is N. Really, that's the amount of gas molecules that you have, or moles that you have. And this, the only way that this can change right here is if you add a gas to it, add more gas to it, or you subtract gas from it. You know, take some air out of your tires, then you would be changing the number of moles. I want to take a minute here to define what pressure is, because gases exert pressure. That's one of the properties of a gas. Well, pressure is defined as force per unit area on a surface. And so if you look at these two sets of shoes, you might ask the question, which shoes would you rather have step on you and why? Well, I know you don't want either one of them to step on you. But of course, these shoes that are up top here, these top shoes right here, these have the force, the area is spread out more. It's going to be the same force if it's the same person that's stepping on you. If these shoes step on you, then a lot of the force is going to be right on the toes and right on this little area right here. And even if we sharpen these up, they'd be even tougher, even a greater amount of pressure, even though it's the same amount of force. So if we change the amount of area, it changes the amount of pressure. Well, you might not think that you can feel it, but gases exert pressure on you every day. It's atmospheric pressure. And it's a good thing that they do because they kind of keep you in the shape that you're in. And so a way to measure atmospheric pressure is a barometer. This barometer is a tube that's filled with mercury, and it's open on the end down in here. And so what happens is the air pressure pushes down on this mercury, and as the air pressure gets higher, then it pushes the mercury higher up the tube. And as the air pressure drops, then it drops the mercury further down the tube. And then as we go up in elevation, we get less and less air pressure because we have less atmosphere above us, less gases above us. So at higher elevations, when we get higher than that, the air pressure drops lower and lower. And that changes things like cooking times and all kinds of things, how long it takes to boil water, and actually the temperature that it takes to boil water. These gases, this atmospheric pressure, plays a huge role in our lives that we don't even recognize each day. There's also a method to measure a gas that you have enclosed. If you have trapped in a cylinder or in a bottle or something like that, and you want to measure the pressure of that, then we use something called a manometer. And the manometer has the gas sample inside of this container, and as you open up this valve and allow the gas to escape, it'll push that mercury. This is again mercury. Mercury works very well for finding pressure. It'll push it, and you find the difference between the level on one side and the level on the other side. Really, you're comparing it to atmospheric pressure to tell what the pressure is of the gas inside of the container. Well, all that stuff applies to gases because we need to measure the pressure on gases. And sometimes we need to change between one unit and another. And so these are pressure conversion factors. Really what these mean are, you need to write these down. These are all equal to each other. 1 atmosphere equals 760 millimeters of mercury, which is the same as 760 torr, which is the same as 101.325 kilopascals, or 1.01325 times 10 to the 5th. That's 10 to the 5th right there, pascals. Or 14.700 psi, which is usually what we use here in America, the psi, pounds per square inch. So you're going to want to have those pressure conversion factors written down because sometimes we got to do a simple action line just to convert between those. Now, something that I want you to do, though, on your notes is make sure that you put stars next to this standard temperature and pressure, and underline or circle STP, that's standard temperature and pressure, because I will refer to that every once in a while. Students always get lost on that. If a problem says convert this to standard temperature and pressure, they think they don't have values, and I'll say something like look to the stars, and here's where the stars are right here. The standard temperature is always going to be 273 Kelvin, which is 0 degrees Celsius, but we use Kelvin every time for gases. And standard pressure is 1 atmosphere, or any of these up here, because those are all equal to 1 atmosphere. So make sure you have those written in your notes and starred so that we can find them very easily. So here's a couple sample pressure conversions that you might see. They are done easiest with the simple action line. They're nothing like what we did for stoichiometry here. But you start out with what you're given on this first one, 13.197 psi. And then, of course, we copy down the psi down here. We want to go to kPa, and on our last slide there, we had that 14.700 back when we said those pressure conversions is 101.325 kPa. And so when we do this, the psi's cancel out, and we end up with 90.965 kPa. So 13.197 is the same as 90.965 kPa. Same with this one right down here. We have 835 millimeters of mercury, Hg, and we want to convert that to atmospheres, millimeters of mercury and atmospheres right here. From our notes, we have a conversion between these two for every 760 of those, and that is unlimited sig figs. That's not just 2 sig figs right there. Is 1 atmosphere, again unlimited sig figs. So I'm going to put this in 3 sig figs. Millimeters of mercury cancel out. 835 times 1 divided by 760 gives me 1.10 ATMs. And so those are equal. 835 millimeters of mercury is equal to 1.10 atmospheres. So here you go. Here's some practice that I want you to do. You're starting with 745.8 millimeters of mercury. I want it in atmospheres, torr, kPa, and psi. I've got the answers right down here. Here's an example action line. Best I could do on this with an action line. 745.8 millimeters of mercury. Change it from millimeters of mercury to ATM. Really, everything's going to look the same here except for this top thing. You're going to change one time to torr, one time to kPa, and one time to psi. So do those and make sure that you can get those answers, and we'll be ready to go. Bye-bye.